Hi, in a previous video I showed that my Fluke 17B multimeter, which I basically just had sitting in a box here on the shelf, because it's not, it's not something I'd typically use every day. I've got better, nicer meters than this one, but anyway, it looks like it is died. I don't know what has gone wrong with it. It's just been sitting in the box. Check it out. I mean, it obviously, the chipset's working, display comes on. It seems to do, or, it appears to work when you actually turn the thing on, but, nothing. Look, zippity doodah. And no, it's not the test leads. I've tried various functions. It just does not recognize anything at all. Has the input blown or something like that? I have no idea. As far as I know, I haven't used it for, anything serious since I got it in a mailbag way back, quite a few years ago now. And, yeah, I think I did a quick teardown on it once, but that was it. So anyway, let's crack this sucker open and have a look. And of course, yes, this is the made in China Fluke. Just like the original, this actually reminds me of the Fluke 19, which was Fluke's first foray into the Chinese-made multimeter market, just to test the waters. It was the Fluke 19 was, here's a photo of it I grabbed from the internet. I don't have mine anymore, but I bought quite a few of these for work, because at the time they were a big deal. They came out, it was I think it was sub $100, and for a Fluke, that was absolutely incredible. You could buy it in the local Tricky Dick store, and it was Fluke's first entry into, they were just testing the market to see if people would want or like a Chinese made Fluke, and they only sold it in Australia, a couple of other Asia Pacific countries, and that was it as far as I know, and it was a complete and utter failure. Almost every one of them died. They had this fault where the chipset would get killed. I can't remember the details, but every one of the ones I had died. I've got tons of reports of them dead. There were, at the time, this was probably back in the late 90s, perhaps. I think it was a long time ago in a galaxy far away, but yeah, it was a miserable failure, Fluke 19. But obviously, well, yeah, they did a second suck of the Sav, and hey, we can still do this. The Fluke 17B just started out as the 17, then it went to the 17B. I'm not sure. Anyway, let's crack this thing open and see if we can find out what's wrong with it. And yes, the good thing is we have the schematic. Awesome. So if you still got a working Fluke 19B, well, you're one of the real lucky ones. You've got a rare instrument there, because I think most of them on the market died. I'd love to find out the exact reason. It was something to do with the chipset ESD sensitivity or something weird like that. Anyway, this one failing, just sitting on the shelf there, does not instill a lot of confidence in me. Now, I don't know about you, but that non-standard spacing on the amps jack there gives me the heebie-jeebies. Alright, let's crack this thing open. 2 AA batteries, lots of Chinese writing on there. Thankfully, you can understand the fuse ratings. And let's whip it open, see if there's anything obvious in here. Give it the smell test. Nope, nothing smells burnt, and nothing right off the bat. Oh! Look! Can you see what I see? Or don't see? Well, there's your problem. That is hilarious. The screws are not on there. I think this is a massive pebcack. As I said, I think I've done a teardown on this before, and obviously I did not put the screws back in. Well, there it is. I fixed it, and I'm pretty sure it'll now work again. Yep, no worries. Well, I could have just deleted this video, but what fun's that? We've got a schematic. I can salvage this. I can salvage any video, no matter how tragic it is. All right, let's just, I don't know, have a look at things. Why not? Meh. And I just checked, and yep, I have actually done a full teardown video of this, episode number 344, to be precise. No wonder I don't remember it. I'm going to do this one day. I'm actually going to, produce the exact same video I've done like 5 years ago or something, and I won't even realize. Anyway, yeah, so I won't go into huge detail about the construction of this thing. I've done that in the previous teardown, I'm sure. Suffice it to say that that's one of the wimpiest 10 amp current shunts I've ever seen. Look at it, this little anemic thing. And the other thing that strikes me about this is, of course, these adjustment pots. Look at them, 1, 2, 3, 4, 5, 6. Is there, have I missed one? 7, 8. 8 adjustment pots in this thing. They're adjusting for everything. Why are they doing that? Well, like every modern multimeter, no longer has. They're all closed case, what's called closed case calibration. You don't have, there's no pots inside to actually trim. But this thing has trimming for almost everything. Why is that the case? Well, it's just using a single chipset here. We'll have a look at the actual chipset itself in a minute. But so it's just a regular, like off-the-shelf multimeter chipset. There's no secondary processor that actually, because basically multimeters can come in 2 varieties. Well, probably 3 varieties actually. One is just like this one, as simple as it gets. One multimeter, specifically purpose-designed multimeter chipset. There's 3 or 4 manufacturers on the market who make these things, and it does everything. It does all the multimeter range switching functionality, measurement, ADC. It drives the LCD, everything else. Does the whole shebang. The second one is to use a multimeter, which is probably more popular these days, especially in the mid to high range meters, is to use a specific multimeter chipset, but it's only a front end chipset. So it only does the measurement hardware, the front end, the range switching, the ADC, and, various generators and all that sort of stuff. And that is just a front end. It can't actually do anything itself. It's not really a processor, can't drive an LCD, can't do anything else. Usually a serial output, which then goes to a secondary processor, which then drives the LCD and everything else. Now we can actually do a comparison with the new EEVblog meter, the BM235 here, and have a look at this one. And you'll notice this one actually uses 2 chipsets here, but this one is a little bit unusual. Usually when you see 2 chipsets like this, you'll have just a multimeter front end chipset like this, which doesn't contain a processor. It's just, as I said before, like the range switching, everything else, the ADC, all that, all the stuff, the true RMS converter, everything else, all the other functionality required for a multimeter chipset. I'll put a typical data sheet over here of a chipset which is fairly common, for example. Now, this one, you would think that that's the case, and it interfaces with the processor over here for the serial, but this one's a little bit unusual in that, no, this one is actually a processor and does everything just like this one up here, but it obviously does, it's designed for closed case calibration. It's got E2prom built in because it's got to store the contents. And it either has E2prom built in for the to store the software calibration functions, or it can use external E2prom. But this one actually is this secondary chipset here. I'll link in the data sheet here, and it's actually just an LCD controller chipset. So obviously couldn't get enough pins on this thing. They needed, even though it's a complete multimeter chipset with processor and everything built in, requires external LCD controller. So this one's a little bit unusual in that respect, but it's more common to find a multimeter chipset and then a secondary processor. Now there's nothing stopping a single chipset multimeter like this one up here from having closed case software calibration, but the actual processor inside here is not designed for that. It's bare bones. It's designed not to have any of that closed case calibration, i.e., E2prom built in, so it can store, calibration settings and things like that and compensate. It's designed to use these external trim pots around here. So in that case, it's a poor choice by Fluke in a modern multimeter to have to require pots like this to trim, just from a long-term, you know, drift characteristic and everything else. It's poor form, not when, you know, modern processors can handle these sorts of things. But hey, that's typical of these really cheap-ass low-end chipsets like this. They require these external pots. And for those who want to know what the front-end multimeter chipset on the EEVblog meter is, sorry, secret squirrel. So anyway, I think that's pretty poor having these trim pots on a modern multimeter. Just, yeah, fail. Anyway, now let's take a look at the schematic. Now, I'll link in the complete schematic down below. It seems to be the official one, so I'm not sure, proprietary. Sorry, Fluke, but once it's on the internet, it's on the internet. So, yeah, there you go. 2009 it was generated. Anyway, yeah, so it looks to be a genuine. It's not like a reverse engineered or anything like that, and I'll link in the PDF down below. Now, the chipset in this thing, they've mangled somehow. I don't know, when they converted to PDF, they mangled that, but it's actually an FS9721, the LP3 version, and I'll link in the data sheet for this puppy down below. And yeah, it's a complete multimeter chipset. FS is Fortune Semiconductor. They're one of, you know, 3 or 4 different makers of multimeter chipsets that are still around, these specialist chipsets. And as you can see, you know, it pretty much handles everything. It is a single chipset, one chip to rule them all, and just miscellaneous stuff around. So let's actually just have a quick look at this schematic and see what we can see here. First of all, take a look at the current jacks here, and I have done a separate video on multimeter input protection. So if you want to know all about fuses and how they do things in this diode bridge here and things like that, which, by the way, is just clamping. That's basically what they're doing there, clamping the voltage. Then I'll link that one in as well if you haven't seen it. It's well worth a look. And look, they're actually trimming. These are the shunt resistors, okay? So this is here's the 10 amp input here. Here's our common jack, okay? So our 10 amp goes through our HRC fuse, of course, into our typical 10 milliohm shunt resistor. That's that real wimpy. Look at it. It's real wimpy. Look. Oh, sorry, I've got fixed contrast, fixed exposure on the camera here. That's why it's all dark. It's very difficult when you're doing white paper like this. You've got to set manual exposure on the camera. Anyway, 10 milliohm current shunt, which is all fine and dandy, and then they're doing a trim across that. So typically, which actually is... okay, you could probably argue that one's not that bad. So they're doing a divider here. They're doing a voltage divider. There's a 100k resistor 47. They're actually trimming that. That's a large value. That's a large trim range. That's absolutely massive. So yeah, I would have limited that. I think that's a bit of poor design work there. Anyway, usually they physically trim the nichrome wire current shunt. Typically it's made out of nichrome wire, the current shunt, and they'll physically trim it either by taking a little chunk out of it or adding some solder, you know, getting some pliers on there and just giving it a little crimp or something, just to, you know, change the value by, you know, half a bee's dick or something like that. So they've decided to add a trim pot, and that's rather unusual. Most companies just decide to trim it some other way, or with the modern chipsets just software trim, of course. Okay, so on the milliamp range here, here's part of the range switch. They've got this range switch actually split all the way through this schematic, as you'll see. And what this is showing, these are the physical contacts on the PCB. So when you put it in the milliamp position down here, it's shorting out these two contacts. What does that do? Well, it shorts out this resistor up here. So here's our milliamp input jack. So if this resistor is shorted out, then this 1 ohm resistor here is going to be our current shunt resistor. Actually, it's 1 ohm plus this 10 milliohms down here. And you'll note that they've got a 1K resistor in parallel with that. So they're just, you know, trimming that down slightly because they want to get it down, because you want this. This should be like 0.99 ohms, really. So that's what they're trying to trim it to, because it's in series with this 10 milliohm, 10 amp shunt down here. And then in the microamp range, this contact is moved from here up to the top. So then we've got this 1K resistor in series here. And you'll notice this is 0.1%. This one here was only 1% tolerance for the milliamp current shunt. It didn't, you know, once again, it's all about the temco. It's not about the absolute tolerance, because this thing is actually trimmed. But you'll notice these ones are 0.1% here because there is no trimmer. for the microamp range. So that's why they're using precision resistors in here, because it's actually not easy nor cheap to get a 10 milliohm current shunt resistor. I do that. I use a 10 milliohm current shunt resistor on my microcurrent, for example, and it's an expensive resistor. Even in thousands and thousands of volumes, it's, you know, upwards of $4 per resistor, right? It is really expensive. So, yeah, if you want the precision, you know, straight off the bat, without having to trim the thing, you know, mine's, what is it? Is it 0.05%? I can't remember. Yeah, I think it's about 0.05% or 0.1, no, 0.1% is it? Yeah, that's actually a very expensive resistor. Hence, it's actually cheaper per unit to just have somebody trim this trim pod here. Yeah, labor takes time, but labor's not that expensive compared to a $4 resistor. It just depends on which way you want to do it. So, yeah, they've decided, no, we don't want a trimmer for that, because the 1K ones, these low values, these low values of 1 ohm and 10 milliohms, they're expensive to get in real precision values. But 1K is not. Like, you can get those for 10 cents in volume or something like that, right? Real, fairly cheap, right, compared to these. So, so they're able to use precision resistors for those and no trimmer. And you'll notice the sense voltage here is actually tapped off different position, depends on whether we're in the amps range or whether they're the milliamp range. So they've got another set of contacts on the range switch here, which in the amps range, of course, it taps off from this voltage divider across this 10 milliohm current shunt resistor. In the milliamp and microamp range up here, it's the same contact. Then it taps off the top here, and when it's in milliamp range here, it actually taps through this resistor onto there. So the current shunt resistor is 1K in parallel with 110 ohms, then in series with 1 ohm, in series with the 10 milliohms there. But it's actually strictly not true to say that there's no trimmer for the microamp range here. It's not for these resistors, but because it's still in series with this 1 ohm resistor in parallel with this 1K here, if you actually have a look, if we bring this in here, and we have a look what we've got 1K in parallel with 110 up here. So that's 99.099 and 0999, but I'll leave the rest off. Anyway, it's that in series with, so plus 1 on the 1K here, but that 1K is a trimmer. Okay, so that's actually 0.999 if it's just the 1K, okay, if you haven't trimmed it lower than that. Plus the 10 milliohm current shunt resistor down here, that's a total value of maximum value, not including tolerance, of 100.108. So these two down here this one down here, it's way too small to affect. It's up in the 47K range, you know, orders and orders of magnitude higher than the 10 milliohms, so it doesn't affect it. It's only for when you're tapping off the amps range here. So obviously they have to trim this 1K here. It's going to make a difference. They want that to be like bang on, okay, because this has no software compensation at all. So they want that to trim this value right down here to exactly bang on 100. So that trim pot actually will actually affect both the milliamp and the microamp ranges. And then they've just got two high value input protection resistors here because it's going directly into the chipset there, just for some current limiting protection for the input pins here, in case there's a slight possibility of overload. And they don't have to be precision, of course, because this is high input impedance. That's why you've only got 1% tolerance there, just Joe Blogg's resistors. Now let's take a look at our volts and ohms input down here. This is our input jack, and then we've got 5 resistors in series like this, and they are these puppies in there. There they are. Why have they got 5 like that? I've explained that in the previous video. It's to get a high withstanding voltage. So each resistor has a certain voltage, maximum voltage tolerance. So you whack 5 in series, and you can get effectively a high voltage resistor there, and that's cheaper. 5 of those is cheaper than one big one, which you'll typically find, by the way, ta-da, in the EEVblog meter. There you go. This is more expensive. You notice the isolation slot under there. That's a high compliant voltage ceramic resistor. Much nicer than just the 5, but they get away with it. I mean, nothing inherently wrong with that. And you'll notice that they got 1.5 mm there, and also here. Now, a real educated guess is that this is actually a design note to the PCB layout person to saying we need 1.5 millimeters minimum clearance on these things. That's what we need, because these are the high voltage inputs. So isolate it from everything else. And this one here, 9 millimeters input clearance. Thank you very much. So assuming that we're in either the millivolts DC range, the ohms, or the capacitance range, then these two contacts on the PCB here are going to be shorted, and we're going to be using these 5 input resistors here for that particular mode. And if we follow the yellow brick road here, let's go over another protection resistor here. We've just got some diode clamping here. What are they? BAV 199s, are they? So we've got some diode clamping. And it's also fairly typical, especially in old Flukes. I'm not sure if Fluke pioneered it or not, and I was kind of going to maybe do a separate video on this. It's I'll try and find another Fluke meter schematic here, which actually shows these. And yes, I actually found it. Here's a schematic from the Fluke 77 Series 3, which actually comes from way, like even much earlier multimeters. I think the Fluke 45 had it, and you know, all sorts of real old school Flukes have this dual transistor arrangement where it's basically they're configured as back-to-back diodes. So it actually uses the breakdown voltage of the transistor to actually act as a Zener, and then having the two actually acts as a back-to-back Zener, because one will have the forward drop and the other one will actually have the breakdown as the Zener, depending on whether it's positive or negative input. And it's a rather unusual configuration, but very popular. So I'm not into, if anyone knows the history of that and whether or not Fluke actually pioneered that, then I'd love to actually know details on that. Anyway, back to the 17B here. Yeah, they've just decided to use some BAV 99s. Meh. Now this part down here is rather interesting. It's a different configuration to what I was mentioning before with the back-to-back Zener clamp in there. But look, if you put it in DC volts or AC volts mode, then it's basically shorting out this, right? So there's nothing there, effectively nothing there at all. But what they're doing is actually tying VSS. Effectively, this is where they're coupling VSS into the common terminal. The common is actually the terminal over here. So the battery negative, VSS is actually the battery negative. If you go up here, there it is. So they're not directly shorted together. They're tied through this 1 meg resistor here. And on the base of this transistor Q1 here, they've actually just got a reverse biased diode there on the base of that thing, and they've got a PNP here. So it's basically they're shorting out that. This goes up to, if you follow it up, yellow brick road again, it goes up to the bottom of our resistor divider here. So these are our range divider resistors here, handled by multiplexing inside the chipset. And basically the common of those is shorted down to ground when we're measuring AC and DC. But when we're measuring ohms, it disconnects the ground, and it's, you know, it's activating this part on the lower end of this resistor network here in the ohms mode and the capacitance mode here. In the volts DC mode, they've got an AC coupling cap here. They actually and a series resistor, so it's almost like a little snubber. They're shorting that out, and then our input goes, by the way, through a PTC, positive temperature coefficient resistor, which will increase in value in overloads, and that's that puppy down in there. Sorry, silly thing. There it is. There we go. There's our input PTC resistor, and then our big 1K. Here we go. This is where they have a note saying install either one of these. Install that or install that. So they've got this 1K resistor here in series. That's very common input protection for, you know, it pretty much handles, this is why you can put mains on the ohms range, for example, because you've got the PTC resistor here, which will increase in value with any overload. You've got the big beefy 1K high voltage resistor here, And no worries whatsoever. And with clamping and everything else inside here, then no worries whatsoever. Because when we're in the ohms range here, by the way, we need to force a current out into the positive jack out here. So that's why it's switching. This range switching is both used for DC and AC voltage ranges plus the ohms range as well. It's rather quite clever. So they're actually switching that in this particular circuit in here when they're generating the ohms. So, you know, it's like constant current type thing out for the ohms range. And likewise for the capacitor too, because basically when you measure how they do the capacitance measurement, they just basically have a constant current output, and then they just chipset just times how long it takes to charge up. Bingo, you can work out the capacitance. And then of course the way that they're tapping that off, not only do they have to generate the constant current from here like this, but they also have to read back off as well. So that's why in the ohms range here, also, bingo, it's tapping off like that. So that's the voltage sense in there, and the chipset can actually measure the voltage across the resistor under test. So I think they're attempting to do some sort of clamping here in the ohms and the capacitance mode, but to what end? I'm not entirely sure, because at low voltages, this circuit is not going to engage. It's not going to do anything. So, you know, at a couple of volts that we're talking about when you're operating the ohms mode, then this is not going to do anything. But at higher voltages, yeah, it's going to start to conduct. So, yeah, presumably some sort of attempt at clamping. And this is not a true RMS multimeter, so there's no true RMS converter chip, either a separate analog device is one, which is quite typical, or the EEVblog meter, for example, is a true RMS multimeter. There it is, but you won't find your traditional analog devices true RMS converter chip in here, because it does some clever stuff using external components in the main multimeter chipset. Might have to do a separate video on that one day. Anyway, this one's an average responding meter, and here's the AC average responding circuit control via the chipset here. And bingo, another trimmer in there for the AC calibration. Bloody trimmers, dodgy as. And it looks like they've got a amplifier in here. Yep, OP, that'd be op amps. So they've got some internal op amps in here. So you'd have to look at the data sheet to get the internal arrangement for this. But basically, so they're our feedback resistors for our non-inverting op amp with a ×10 gain there. Now, some multimeter chipsets, they'll have a combination of standard op amps in there, plus they might have a chopper amp in there as well that you can select with the internal mux in. So that's, you know, not uncommon because the chopper amp, very precise, you know, no bugger all DC offset. So you might find those on, say, a higher end 4.5-digit multimeter chipset. And there's our DC calibration trim pot. Looks like is that hooked up to 2 reference pins. We really need to look at the data sheet for this, get an internal block diagram to get more fancy-pantsy. Speaking of fancy-pantsy, look at this. This is quite unusual. You don't often see this in a multimeter, so thumbs up to this. We've got cold junction compensation, and that's for the temperature mode. So you'll notice that when we select temperature on the range switch here, bingo, it goes up to here, into this amp here, but then that's offset with a cold junction compensation. I've done a video on cold junction compensation, so I won't go over it again, but awesome. And that's what high-end thermocouple amplifiers and thermometers like, hang on, I've got one here somewhere, like this Fluke K-type Fluke F3000. I've done a teardown of this and various others, and these have cold junction compensation on the input pins here. They have a temperature sensor which takes into account the temperature of the dissimilar metals, which can cause offset errors in your temperature. So they've actually added that in here, and you'll notice, look, there it is, a temperature sensor. And once again, the designer has put a note in here for the PCB person, place near the inputs, because it's got to be right near the input jacks. Brilliant. don't know why they bothered doing that, but it's excellent. I mean, this thing's, you know, it shows they've tried to build it down to a cost, but hey, cold junction and compensation, brilliant. And you'll notice, there it is, U4 down there. There's our little temperature sensor right down there. But really, you know, in this case, it doesn't, like, matter. In your proper ones, like that other Fluke thermocouple meter I showed before, it actually physically couples the chip through to the metal of the input jacks, and this one's just physically close. It's not doing that, so it's, you know, it's a little bit how you're doing, but it's, I guess it's better than halfway up the meter, but yeah, in the scheme of things, doesn't really matter here. But yeah, they've gone to that effort, so I'm very, very surprised. And they've got a offset trim pot in there as well, just for the temperature. So they, you know, they really did take this thing seriously. I guess maybe not surprising. I mean, it does have a specific, you know, maybe that was a big selling point they wanted to do. This thing does temperature and does it probably better and more accurately than your average multimeter. There's not much else doing here. We've got some miscellaneous, looks like some filter stuff maybe happening around here. There's our main oscillator, 4 megahertz, and direct LCD drive up here. And Bob's your uncle. That's about it. Some extra range, you know, the buttons and things like that, some extra range stuff, and, well, not much. Well, what do we got here? A mux. Yeah, there we go, 74HC148 priority encoder. So they've basically got some pull-ups and pull-downs here, just the range switching. So they're basically just detecting which, so the chipset can detect which range is actually currently selected. So there you go. I hope you enjoyed that. Hopefully I managed to salvage this video. It was supposed to be a repair of this thing, and sorry, Fluke, I thought this thing had come a gutser and failed on me, but oh, it was a pebcac. Screws when I previously put the thing after the teardown. Oh, those things happen, you know. Oh, geez. So that was better than deleting the video, I hope. Anyway, hope you enjoyed it. If you did, please give it a big thumbs up. Catch you next time.